Knowledge distillation is improved in this paper by forcing teacher to split classes into subclasses and learning the student on them. This paper is from 2020. It's called Subclass Distillation. It's from Muller, Kornblith, and Hinton, Geoffrey Hinton. Abstract. After a large teacher neural network has been trained on label data, the probabilities the teacher assigns to incorrect classes reveal a lot of information about the way in which teacher generalizes. By training a small student to match these probabilities, it is possible to transfer most of the generalization ability of the teacher to student, often producing a much better small model than directly training the student on training data. The transfer works best when there are many possible classes because more is then revealed about the function learned by the teacher. But in cases where there are only few possible classes, we show that we can improve transfer by forcing the teacher to divide each class into many subclasses that it invents during supervised training. The student is then trained to match subclass probabilities. For datasets where there are known natural subclasses, we demonstrate that the teacher learns similar subclasses and these improve distillation. For click-through datasets where the subclasses are unknown, we demonstrate that subclass distillation allows students to learn faster and better. Okay, in this work we focus on distillation for datasets. There are only a few possible classes, resulting in limited information to be transferred. We show that we can improve the transfer by forcing teacher to divide each class into many subclasses that it invents during supervised training. We propose an auxiliary loss that encourages each subclass to be equally used while ensuring that each prediction is peaky. We show that experimentally that subclasses learned have semantic meaning and help distillation. The subclasses also can be used to interpret the model's predictions by clustering them into discrete bins. Conclusion. We propose subclass distillation and distillation method where the teacher divides each class into many subclasses it invents and the student matches the subclass probabilities. By the way, just shortly, the way how they split force the teacher is that they use softmax, where to each class they add additional S dimensions, and then they force each prediction through the softmax, and then they also add extra loss to make sure that the probabilities in different classes, in different extra dimensions on each class subclass is equally distributed. Okay, subclass probabilities. We show that we can improve learning compared to conventional distillation and penultimate layer distillation in terms of generalization and or training speed. We show that with simple auxiliary loss, our teacher divides exams into datasets in semantically meaningful classes. The loss encourages the subclass prediction to be confident and diverse. We showed that when the underlying subclass structure is known and matches the choice of number of subclasses, cipher 2 times 5 and MNIST 2 times 5, we can discover the original subclasses with high accuracy. The subclass distillation outperforms other distillation methods. When there is a subclass structure in the dataset, it does not match the original subclass chosen, sub A. Our method is still discover semantic subclasses, which helps subclass distillation. Finally, when there is no known subclass structure, Kiriteo, subclasses can provide faster transfer and more bits per example when the data available is limited. Further validated, the subclass distillation provides additional bits per example by showing on MNIST that we can learn to predict binary label without any binary supervision, just by mimicking the intraclass teacher subclass relative probabilities. Alright, so this was the spice of the paper. The spice that must flow. I hope you liked it. I will now go more into the detail, so please don't like and don't subscribe, and if you'd like more details, let's continue now. So introduction. The idea of compressing teacher model into smaller model is one by matching the predictions of the teacher was introduced in Bucciolo et al. 2006. After training the teacher, they performed the transfer of new unavailable data, minimizing the squared difference between the losses of the final softmax of the teacher and the student models. A related technique called distillation was introduced by Hinton in 2014. That paper performed the transfer on the labeled training data rather than on new unlabeled data. The student is trained to minimize a weighted sum of two different cross entropies. First is the cross entropy with the correct answer using the standard for softmax. The second is the cross entropy with the probability distribution produced by teacher when using a temperature higher than 1 in softmax of both models. The point of which is a higher temperature is to emphasize the differences between the probabilities of wrong answers that would all be very close to 0 at temperature 1. There have been since some interesting theoretical development of distillation, Lopez et al. 2016, and it is now being widely used to produce small models that generalize well. There are needed for resource-constrained applications neural networks such as text-to-speech and mobile on-device convolutional neural networks. In this work, we focus on distillation for datasets. There are only a few possible classes, resulting in analytic information to be transferred, for example, binary classification. We show that we can improve the transfer by forcing the teacher to divide each subclass into many subclasses that it invents during the supervised training. We propose auxiliary laws that encourages each subclass to be equally distributed while ensuring that each prediction is PK. We show that experimentally that subclasses learned have semantic meaning and help distillation. The subclasses can also be used to interpret the model predictions by clustering them into discrete bins. The paper is organized as follows. We start with the description of subclass distillation, comparison-related method, penultimate layer distillation. First, we train the models on binary split cipher 10, and we call cipher 2 times 5, where we group sets of 5 classes together to create a binary classification task. We show that the teacher trained to produce subclasses is able to discover the original ciphers and classes, despite receiving only binary supervision. We also show that distilling from this teacher using these learned subclasses leads to better results as compared to the conventional distillation and penultimate layer distillation. We move next to the Celeb A datasets, Liu et al. 2015, in which each example has 40 binary labels. We show that when predicting single one of these binary labels, the subclass produced by the teacher are highly correlated with the other binary labels it has been trained on, which helps subsequent class distillation. We conclude the experimental section with 2 additional results. First, Crito click prediction dataset. 2017, we show that the subclass distillation outperforms conventional distillation in terms of training speed. We also show that when the student does not see full dataset, subclass distillation provides significant generalization gains. Second, using MNIST 2 times 5, we show that the student can learn to predict the binary label by learning to predict the relative subclass probabilities intraclass without having ever seen the binary labels or receiving class relative probabilities from teacher. Okay, subclass distillation. During distillation, the amount of information the student receives over generalization tendencies of the teacher network depends on the number of classes. The information provided by the hard target labels is logarithmic in terms of number of classes, but the information about how teacher generalizes is linear. The number of classes provided linear number of classes provided that we distill using the logits using cross entropy at high temperature. This means that distillation is considerably less efficient for models with few classes. Binary classifiers are important in many applications, and the aim of this paper is to make distillation more efficient for such models by forcing the teacher to invent S subclasses for each of the C classes in the dataset as shown in figure 1. The teacher computes C times S logits and puts these through a softmax to get C times S probabilities that sum to 1. The probabilities of all subclasses of a class then added to get teacher's predicted probability for that class. The teacher trained by minimizing the cross entropy with the class probabilities. So then they have a loss here that is an average over a number of examples, summing over the classes. Then there are the labels inside of the sum. There are labels times log of sum over subclasses of a given class. Example, yeah. Given logits that the output probabilities P are computed in usual fashion by performing a softmax operation over all logits belonging to the same example. The temperature parameter 3 controls the entropy of the output distribution. When training the teacher, it is set to 1. When distilling the knowledge from teacher to the student, it is often beneficial to increase the temperature. In subclass distillation, it is as in conventional distillation, the students train to match the teacher. However, rather than use only C classes in the original dataset, the student learns to mimic teacher's outputs of C times S subclasses. Like teacher, the student produces C times S output probabilities P for each example, I resulting in subclass distillation loss. And yeah, of course, here we have in short, average over all examples, over all classes, over all of their subclasses, and then we have the probability times log probability of the student, where we scale the loss by temperature to the power of 2 in order to keep the gradient magnitudes approximately constant when changing the temperature, Hinton 2014. Thus, with this loss, the knowledge is transferred from teacher to student on very few probabilities the teacher assigns to the subclasses in the original dataset, but also through probabilities assigned to the subclasses. When the training student, we typically use combination of distillation loss, loss distill, and the standard cross entropy loss X and where alpha controls the balance between hard and soft targets, and we call this task balance. Penultimate layer distillation. An alternative to subclass distillation also incorporates more information into the distillation. It's not to distill from the logits, but from the penultimate layer activations, from the other layers, as in Romeo 2014. In this case, and of course, penultimate layer, the student is linked in the distillation phase. Now the student use capacity. In the subclass distillation, the subclass logits are the prediction of teacher's penultimate layer activations in the lower dimension, which is learned during the teacher's training phase. Therefore, the prediction into subclasses can remove irrelevant information present in the penultimate layer, while retaining more information compared to the class logits. Note that Hinton 2014 shows that minimizing the squared difference between the zero mean logics of the teacher is the limit of distillation as temperature goes to infinity, provided that the learning is also squared temperature. Therefore, the subclass distillation as temperature goes to infinity is equivalent to penultimate layer distillation applied not on the full penultimate layer but on low-dimensional projection of the layer. Auxiliary loss. In subclass distillation, the cross entropy loss constrains only class probabilities and not the subclass probabilities. Without additional loss encouraging the network to use all subclasses, it may consistently assign high probability to single subclass of each subclass and assign extremely low probabilities to others. In this case, the subclass would provide almost no additional signal for the distillation. Thus, we propose auxiliary laws that encourages the network to assign different examples to different subclasses, even when they belong to the same class. Given the mini-batch and logits of vectors, we compute auxiliary laws. So auxiliary laws here is average of average of log of something like softmax, where the mini batch of analysis where the vectors where softmax of dot product of it's basically norm of the vector logit vector norm square norm of the logit vectors divided by temperature, ZE, I'm not sure what, where VE is normalized version of VE. Zero mean unit variance. To prevent easy solution of the minimization, making the logit large. The above T is a temperature hyperparameter, although its value need not to correspond to the temperature used for distillation. This auxiliary loss encourages the normalized logit vector corresponding to each example to have low dot product with other normalized logit vectors. In practice, the network accomplishes this by distributing examples across subclasses. And then they use beta, they multiply the auxiliary loss with beta and add it to the loss of the teacher. So let me have a look once more. So in each batch they make sure that the dot product of the examples that let me read this again. This auxiliary loss encourages the normalized logit vector corresponding to each example to have low dot product with other normalized logit vectors. Oh yeah, I think I see it because it's not softmax, right? It's something else. Yeah, it's something slightly else. So basically, what they do that they yeah, never mind. I think it's not something extremely difficult. With more focus, you can write it yourself. Basically, they do this exponential, making sure. Well, it's yeah. You have to just read the equation. Experimental results, cipher 10. So as I mentioned there, they use cipher 10. They split it into two binary classes, and while still having the still knowing the subclasses of two binary classes, and then looking at the subclasses discovered, and what they say here is finding the nearest neighbor in the network trained on cipher 10 query is a close-up of a horse head. If the nearest neighbor is calculated in the class logit layer, find example from the same class horse, but semantically similar image with a close-up head only is only the fifth nearest neighbor. If the distance is calculated in penultimate layer, all nearest neighbors are semantically similar to the query. They show that some semantic information is lost in the class logits, and distillation can benefit from more information. We train ResNet with 20 layers to be used as a teacher, and training details of parameters over there. If you train network classification task, like get, so they get plus 1% accuracy, 1.3 accuracy gap between them in the binary classification task, and the benefit of using supply information in one, even when the evaluation is done at the class level. Next, we investigate how making teacher event subclasses affect the network performance. These 10 subclasses, although the result of 39.3% is far better than the chance 20%, we observe that since there is nothing encouraging the network to use all subclasses, they can die during training. The subclass accuracy can significantly be improved by adding auxiliary loss, which increases the accuracy up to 64%. Note that this network has only seen binary labels, but is able to separate the classes in the meaningful subclasses without extra supervision. Figure 3 shows how the best network out of 3 runs splits the subset of example in the validation set into subclasses. Most errors arise in distinguishing among cats, birds, and deer, while other subclasses correspond to the original dataset. For comparison, the state-of-the-art 2018 only unsupervised classification on Cypher 10 is 57%, so they got 20% boost. Using the environment information about the clustering method, I see. Here we show that with little extra supervision and binary labels, we can outperform this result with very simple approach. Subclass distillation. In this section, we investigate how to transfer teachers' knowledge to low capacity. With pick XNA distillation, we observe a gap of 2.2%. Training speed. Yeah, I'm running out of time. Let me see this criteria. In our set of some experiment, we ignored some of the available supervision during training time and instead used it for evaluation in order to verify that our approach learns meaning for subclasses. In a real world scenario, we use all the available information for training. Therefore, we also tested our approach on binary datasets without known subclass structure. The critical click prediction dataset. Dataset consists of unanalyzed real valued and categorical features. The target is binary, indicating whether the ad was clicked. Subclass distillation accelerates training of corridor dataset and leads to accuracy improvements when limited data is used for distillation. We use the large version of the dataset and we downsample on non-correct examples to create balanced dataset. The teacher is 5-layer fully connected network achieving 71% accuracy, while student is 1 hidden layer network achieving 71%. Note that the tiny accuracy improvement is significant in the click prediction task since it results in large revenue increase for large user bases. More important, subclass distillation again trends faster, provides more information about the teacher. Take an example, but the data is so big it doesn't affect the final performance. Right. That would be all. Let me read quickly the conclusion again. We propose subclass distillation method where the teacher divides each class into many classes. That is, when the student matches the subclass probabilities, we show that we can improve learning compared to the combination, destination, and penultimate layer distinction in terms of generalization and training speed. We show that with very simple auxiliary laws, our teacher divides examples of the data into semantically meaningful subclasses. The laws encourages the subclass predictions to be confident and diverse. We showed that when the underlying subclass structure is known and matches the choice of the number of subclasses, Cypher 2 times 5, M is 2 times 5, we discovered the original subclasses with high accuracy and subclass distillation outperforms other distillation methods. When there is a subclass structure in the dataset which does not match the number of subclasses chosen in celeb A, our method can still discover semantic subclasses which help subclass distillation. Finally, when there is no known subclass structure, subclasses can provide faster transfer. More bits per example when data is available is limited. We further validated the subclass distillation provided additional bits per example by showing on MNIST that we can learn to predict the binary label without any binary supervision, just by mimicking the intraclass teacher subclass relative probabilities. Okay, you made it to the end. Thank you very much. Hope you like it. Please never ever like or ever subscribe. No, it's a joke, of course. But I hope you like it, and yeah, see you next time. Bye, bye, bye.